Hello, this is Jack Jackson back again. We're going to pick up where we left off talking about quadratic expressions, quadratic polynomials, quadratic functions. We're actually going to start looking at quadratic functions now, and we're going to look at the relationship between factors and x-intercepts and roots. So the idea here is to take some of these things and graph these together. So let's take f of x equals x plus 2 times x minus 3, and I'm going to graph it here in Graphmatica. So y equals x, what was it, x plus 2 and x minus 3? Yes. X plus 2, x minus 3. Now, there's the graph. Okay, that's interesting. Okay. And the thing to note that we want to notice here, I'll emphasize it here a bit, is a couple of points here. I want to emphasize the point notice that when x is negative 2, y is 0, that's a point on the x-axis. And when x is 3, y is 0, that's also a point on the x-axis. We can see those two interesting points there. And we can see them up here in the formula because in the factored version it's pretty easy to see that if you plug in x equals negative 2, the first factor is 0, and it doesn't matter what the other factor is as long as it's defined, the product's going to be 0. And likewise, when you plug in 3 in the second factor, it's going to make it 0, making the whole thing equal to 0. So it's pretty easy to see that those are the only two y values, only two x values that are going to give you a y value of 0. Let's back up a minute and look at linear equations. If I have 2 times x minus 3, notice that that's going to go through that same y-intercept of x equals 3. So in general, when I have a factor, every time I have a factor, it corresponds to a root. And these quadratics are going to have two factors, typically, most of the time. They're going to have two factors, hopefully, sometimes two different ones. And that's going to give you these two places it crosses the x-axis. So let's do a couple more. If I say, what if I do, say, x plus 3 and x minus 3, what's going to happen there? Well, the x minus 3 is going to go through the x equals negative 3 and x. Well, in fact, let's just do them separately. X plus 3 goes through negative 3. X minus 3 goes through positive 3. But when we multiply them together, it's going to go through both. Both of those places. Now, what happens if I let's do some other things. Suppose I take this now and put a coefficient in front. Well, let me graph that one back again. What's going to happen if I put a 2 right there in front as another factor, but a constant factor this time? Well, we know that's like taking this equation that I already have graphed, that function, and replacing y by y divided by 2. So really we're going to multiply the y's by 2, which is going to stretch it. Now I can't see it on this particular screen, but it does go down here below the axis. Okay? So notice that's it. 1, 2, 3. And let me go ahead and change this now. Let's see if I can get it to go through my two original points that I had graphed there in red. Let's go back to that one. It was x plus 3, I think, and then x minus 2. No, x minus 3, I think, and then x plus 2. And I think that was going to show those 2 points. And notice again, if I put a constant in front of here, if I put a half this time, now it's going to be half as tall. If I put a 2, it's going to be twice as tall. If I put a 1/5, it's going to be 1/5 is taller. Actually, it's infinitely tall. It's going to be 1/5 of the way closer to the x-axis. But what happens if I put a negative there, like -1? Well, that's going to take the original and flip it over the axis. And if I put a -3 there, it's going to be flipped over the axis, or -1.2. Okay, and notice all of these have the same intercepts. Okay, so the x-intercept anyway, not the y. So notice that those factors determine your x-intercepts. So some different terminology. If we just talk about, say, the polynomial x plus 3 and x minus 2, each one of these things is called a factor. Right? And then if you say x equals -3, actually, let me do it this way. Let me just do it as a set. If I just say x that's in this set, -3 and 2, these guys here are called roots or zeros of that polynomial. Okay? But if I put y equals that, now I have an equation, or if I would rather, f of x equals this. I have an equation which represents a function. So this is a quadratic polynomial. These now, when you put y equals, are quadratic functions. Okay, and then these are solutions to the equation 0 equals x plus 3, x minus 2. So here we have an equation with 0 there, and so these are solutions. They're called roots or zeros of the polynomial. And as far as this quadratic function here, they correspond to x-intercepts. So here they are x-intercepts. So it's really saying the same thing, it's just different ways of saying it. So these are x-intercepts. They correspond to factors of the polynomial, which correspond to roots of the polynomial, which correspond to solutions of the equation when you set y equal to 0. So those are all different ways of saying the same thing, basically. But the terminology is that way. Okay? So notice they have two factors, and they touch the x-axis twice. And the constant factor has nothing to do with the x-intercepts. It doesn't change that, but it does have to do with the vertical stretch or compression. Now, we can start by thinking of constant functions, and the most basic one, I guess, is y equals 0, and all constant functions are just vertical shifts of that. Y equals 1, y equals 1.3, y equals -2.7. They're all just shifts of each other vertically. Turns out you can take y equals x. Every linear equation you can get to be a transformation of this. You can do it a couple different ways, but if we think of it as the slope y-intercept form, we can first change the slope, let's say make it y equals 2x, which is a vertical shear or a stretch, and then we can add the y-intercept out here, and we just did a vertical shift of that. So we went from the y equals x, the maroon one, which was our original, we stretch it or compress it, shear, strain is the right word, a vertical strain, to give you the blue one, the dark blue one, and then a vertical shift to give you the other one. So all functions can be thought of this way, possibly with a flip, right? So if I start with, again, with y equals x, there's the maroon one, and if I put, say, a -3 there, it not only stretches it by a factor of 3, but it also flips it over the axis, and then I can add my coefficient. and shift it up and down. So we can think of all linear functions as just starting with y equals x and transforming it. Well, we can certainly take y equals x squared and transform it, and we can get some of the same kinds of things. Okay, so if we start with y equals x squared, what kinds of things can we do there? Well, let's see. One thing you could do is let's do the x first. You could put the x in parentheses and add or subtract a number to it, like say x plus 2. That'll shift it to the left 2. And then I can put a number in front like, let's say about a half. And now that's going to squish it down closer to the x-axis. And then maybe I can add something at the end, like add let's add a negative 5, and that'll shift it down 5. And so we can see that this new equation, 1/2 times x plus 2 squared minus 5, is going to be a new quadratic thing that's just a transformation of the y equals x squared. So in general, if we start with y equals x squared, we can think of it first by taking x minus h squared, and that's going to translate it. And then we can think about putting a here, and that's going to be a vertical stretch, maybe a flip if a is negative. It will be a flip if a is negative over the x-axis. And then finally we can add a k here. And you notice that this is just a transformation of y equals x squared. And you also notice that the key point here was 0, 0, and it gets translated to, translated, shifted, whatever happens to it, to the new point, which is going to be hk. So hk is going to be our local extremum, which we call a vertex. So that's going to be the new vertex. H is how much we horizontally shift, k is how much we vertically shift. And so, and then the stretch here, really, you could do the stretch first, actually. I could do that in a different order if I want. I could actually go do the a x squared, do the stretch or compression first, and maybe the flip if it's negative, and then do the other pieces. So to here, to here, to here. And notice that first piece doesn't move 0, 0. The next one is going to move it to the right or left by h, and then k is going to be moving it up or down. So there's your vertex. The a determines whether it's been flipped or not. So if a is positive, we're going up. If a is negative, it's concave down. So that hk is going to be right there. It's going to be a maximum there or a minimum there. Okay, so let's take a look at that. So y equals x squared has a geometric shape called the parabola. There's actually a geometric definition of a parabola, but it turns out to be that. Okay, now for example, y equals x to the fourth looks kind of like that, but it's not truly a parabola. So really that parabola term should only be referred to y equals x squared and transformations of it. So we can think about transforming this, and anything that's going to look like what you see in the box here, right here, okay, here we go, let's make it big. Anything that's in that box, that is going to be something that is a transformed transformation of y equals x squared. Okay, well, if the n is square, here it is. So anything that looks like that is going to be a transformation of y equals x squared. Or in general, anything that looks like y equals a times x minus h to the n plus k is going to be a transformation of the power function y equals x to the n. We've looked at transformations of power functions already. Okay? So the question is, can we go back and forth between these two versions? Well, we know we can go this direction. That we know. We know if we have this, we can expand it out and get this one over here. That's pretty easy. But the question mark is, can we go this direction? Can we take anything that looks like y equals ax squared plus bx plus c and get it to look like this? So in general, it's possible to take this if we multiply the x minus h times another x minus h times however many we need n times and expand it out. We get a polynomial whose highest term is going to be ax to the n. Okay. So we're going to get something that looks like this, but maybe with more terms, with the terms going from a 0th term, a constant term, up to an nth term. But the question is, can we take that and go backwards? Well, let's talk about this one right here for just a minute. If you have this, let's recall some basic characteristics. The n is the most important thing because it determines the basic shape of the graph. The h determines your amount of horizontal translation. The k is a vertical translation. The a is the vertical compression or expansion. And if a is negative, it flips upside down over the x-axis. But the n determines the basic shape. So, there's a way to take something like this and multiply something out like this form and get it to be like that. So we know we can do that. The question is, can we go this way? Can we go this way? Yes or no? Well, the answer is yes. We can go both ways if the power is 2. But we'll see in a minute the answer is no. Yes this way no matter what. But it's no this way if the power is 3 or bigger. At least sometimes you can go back, but not always. I'll show you that in just a minute. But right here I'm going to look at one where the power is 2, and that's our focus for right now. So we have y equals 2 times x minus 3 squared plus 4. Okay? Let's multiply all this out. Well, x minus 3 squared, remember you square the first term, square the last term, multiply and double for the middle. That's a trinomial square. Then distribute this 2 across here. 2 times x squared is 2x squared. 2 times negative 6x is negative 12x. And 2 times 9 is 18, and then combine like terms here, 18 plus 4 is 22. And so we were able to go this way. So we know, at least in this case, it's possible to go backwards. And notice we have two forms now. We have y equals 2x squared minus 12x plus 22, so we know definitely it's a second degree polynomial, a quadratic polynomial. And from here we can easily get that if x is 0, y is 22, so we get the y-intercept. We also have another version here, like this, and from this we can easily see the vertex. The vertex is 3, 4. Notice the opposite sign you see here, but the same sign here. The vertex is 3, 4 because it's just a transformation of y equals x squared, and we know what the graph looks like. Because that's a transformation of y equals x squared, it has to look just like y equals x squared with a possible shift.